Okay, everybody. Welcome to the second poster presentation session. 3 posters will be presented here in every time 5 minutes, and then 2 or 3 minutes for questions. So I want to start with the poster on this side, or in fact the 3 posters on a row on this side, which will be presented by Michael Heck.
Yes, thank you for the introduction. Most of you might know Heck Lange as a company providing analytical equipment to the water industry. Maybe not everybody of you knows that we have enlarged our offering in the last 2 years by also offering standardized control modules to the water industry. And if I say standardized, that's the most important word in that 5 minutes presentation, because those modules are standardized. They come along with a manual, they come along with our instruments, and they are very easy and simple to integrate. Those modules are available at the moment for nitrification control, and I will show you an example later on. They are available for intermittent operated plants operating. They are available for phosphorus control. They are available for sludge thickening and sludge dewatering, and they are also available for the adjustment of the sludge retention tile. So we have a large offering for wastewater applications, and those are coming along with our sensors, which you might maybe know. Here I have prepared one application, which was an installation of an NRDC in the UK, in the southern part of the UK. This was one of our earliest applications. And I've selected this example because this was a very nice example. This was a treatment plant, or is a treatment plant, in the southern part of the UK, in Peel Common, or Southampton might be better known. And the nice thing on that wastewater treatment plant was that they have 8 lanes which were running in parallel, and we could then directly compare the performance of our VETOS NRDC to the standard operating procedure of Southern Water. The process which we had to compete against was a so-called Baden-for 4-stage process. And the standard technology or standard process, what is applied by Southern Water, is to have in each of the 4 zones a DO concentration in the beginning of 2 milligrams per liter. The second zone was 2, the third zone is 1 milligram per liter, and the last zone is 0.5. And we had the chance to add our NRTC to the other 4 lanes, so the other 120,000 PE which were treated there, and we could then directly compare the results of our controller against that standard control of Southern Water. And the results are shown here. So basically what we could prove is that the airflow to the part of the plant which was under VETOS control was 25% less than in the part of the plant which was operated at Southern Water standard control, and the 25% less on energy was also related to a similar reduction of energy. Also we have shown here, and you will see that here, that due to the instrumentation and due to the increased transparency, we were able to achieve a better performance regarding the limiting values. Here in that example, you see some events where we had a very high inflow load coming in, so ammonia inflow load, and that our controller reacted very sudden in order to minimize also the effluent ammonia peaks. So what we have delivered here was a system with sensors and with controllers, which in the end generated a payback of less than 18 months and resulted in and also an increased process stability. Those is an NRTC. On the other side, there is a PRTC, a small controller, which we have delivered to United Utilities. This is a controller which helps to minimize the adding of chemicals, precipitation chemicals, for phosphorus removal. And also here, we have proven at United Utilities that we have used less than 45% chemicals compared to the strategy which was in place before. So all in all, the conclusion is we have a lot of control modules available. They are very simple and easy to integrate, and they have proven, meanwhile, more than 150 cases in Europe, that we are able to save energy and also chemicals in a very simple and easy way. Thank you.
Very well in the time, so enough time for questions. Somebody with a question? I have a question. Control, of course, part of control is always the control variables, which has to be tuned, or tuning of controllers. How is that implemented in this controller?
So we have 2 different types of controllers. Once the user interface might be our standard SC1000 controller, as you see here. So all the control parameters for example, for phosphorus removal, what kind of chemical is used, what's the active substance, what the controller parameters are those are added here in that SC1000 display module, and that's the way how we communicate to our controller. Or we also have here some bigger applications where we have a small industrial PC where we are also able to combine several modules in order to have a plant-wide control. And then we have a little different display modules, user interface. But it's also a standardized user interface which we are able to deliver here.
The question was more, who is going to change the parameters to get optimal control?
So for the small control modules, we have a service contract in place. There's also a commissioning procedure. We are, thanks to the SC1000, to all our controllers remotely connected via GPRS, and there is a service contract our customer can order, and then, of course, the tuning of the parameters is done by Hachlange.
Jaap Verschuilen, Veolia. What we face in the Netherlands and also in Germany is that a lot of wastewater boards have a kind of control for nitrogen, for oxygen, that are very enhanced in relation to other countries in Europe. So the benefits for 30% less, I think, couldn't be achieved in the Netherlands. What's your opinion about it?
I agree, savings are always related to the jump-off point, means where you are coming from. But just an example here from Southern Water shows, which was, in my opinion, at least for the UK standard, a very high level of control automation already, because they had that, but then for 4-stage processes, they had a very good working DO control in place. And what we have added was an ammonia-based adoption of the set point. And we were also surprised that we were really able to gain 25% savings. And this was not something which Hachlange measured, that was measured by Southern Water. There's also a report available. And we have measured that 4 lanes against the other 4 lanes. And this means we had 120,000 PE which were saved by us, and the other 120,000 PE, they were operated as a standard procedures. And of course, it's always depending where you are coming from. And then if you go to some Southern European countries, the savings are potentially bigger than in the Netherlands or in Germany. But nevertheless, we also have good examples in Germany. For example, this one here in Rheinhausen, where we have also saved 110,000 kilo euro per year on a simple phosphate removal controller, which is incredible, you would say.
Okay, thanks again. We move on to the next poster. One more round of applause. The next presenter is here. He was lost, but he's found. Before I pronounce his name wrong, I will leave that to him.
Thank you. My name is Jing Liu. I'm working in a company called Bioprocess Control, but also Lund University. And the poster presentation here is an example of a nice instrument, AMPTS, abbreviation of automatic methane potential test. And this actually, it's the instrument to measure the anaerobic biodegradability or biogas methane potentials. And because this is actually a very useful parameter, it has been, it's not something we invented, it's been used worldwide in the academic world. But the problem is it's very labor intensive, and also a lot of labor is involved to do the measurement, a lot of error is introduced. So there's a big problem for this kind of test that can be tried to, well, I would say utilize the industry, is the data cannot be compared at the different lab, due to the reason of the experiment platform is not the same. The measurement principle, sometimes the accuracy, measurement accuracy is not the same, and also the human error is introduced, as well as the data interpretation and the data presenting. And what we have actually present is the one case that AMPTS has developed to basically solve those issues. Basically, we are talking about more friendly user interface for experiment setup, more real-time gas volume and flow rate normalization, because you know that the key parameter for this BMP test, or anaerobic biodegradability, is to monitor the training, the ultra-low gas flow. And when we measure the gas flow and the gas volume, temperature and the pressure have a big influence on the measurement accuracy. So in the optimum world, in the ideal situation, is you do the compensation for both temperature and the pressure in real time. And that's actually the first case. That way, there is such instrument that can do that. And we have also algorithm to avoid the overestimation of gas volume and the flow rate. The reason is because when you're actually doing the anaerobic biodegradability test, you need to create the anaerobic conditions. In that cases, you have to flash the headspace gas using nitrogen, and that sometimes actually create overestimations. And then we have algorithm to do that. And other things, for instance, the remote accessibilities, because a lot of tests, this kind of tests need to be carried out for almost 1 month. And in the laboratory, and people go there and every day to do the measurement and the check. In these cases, actually you only need to do the system setup in the day one, and actually you log in from time to time remotely to check the data to generate a report, and so on. And so it's save a lot of labor and also improve the data accuracy. So the data present here is the one application that use instrument for monitoring the sewage sludge from the wastewater treatment plant. As you can see, the data repeatability is very high, actually within 1%. And we can also monitor the kinetics, the profile of the biodegradability very clearly. We can link to the biodegradability by doing calculations. So as a conclusion, this actually little instrument can solve, I would say, take the quite good step to solve the problem of standardize these measurements, both in the hardware level, but also in the data interpretations and standardizations. Thank you.
Thank you. Do we have a question from Mr. Liu?
Ja, Verschuilen Veolia. Could you use this equipment to optimize your, say, for instance, thermal hydrolysis degradation, and then say, okay, within 5 days, I know where it's going to, kind of prediction.
If I understand what you mean, you want to optimize the hydrolysis of the
guarantee your system.
Yeah, okay. The thing is, this instrument is, all the technology is developed to rather quick estimate to get the idea of substrate characteristics, basically, because that's including how quickly, how much gas you can convert it from biomass to, for instance, methane or biogas, and how quickly this degradation will take place. And for unknown given substrate, this is also give you an answer whether you need some certain pretreatment or not. So in your cases, if you mention you're going to implement hydrolysis steps, maybe that's actually the answer to tell you whether you need a separate hydrolysis steps or you can very simple integrate to the existing degradations. And there is also possibility, we are working on it, we can mention that with this system, because we can get the kinetics very well, we can, by combining some simulation tool, we can also predict the degradation curve. In the first 1 or 2 days, we can predict what's happening after 30 days. And this actually, the accuracy will getting more and more accurate, because as time goes by of the experiment, you get more close prediction, more accurate prediction. And there is also a fine adjustment from the beginning using the real experiment data. So I hope that answers your questions.
Okay, thank you, Mr. Liu. We move on to the final presentation of this afternoon. That is of Tom Wambeck and of Aquafin. I'll give him the floor.
Hello, so my name is Tom Wambeck. I'm from Aquafin. and I'm presenting Epigone. That's actually a combination of two words, Epi and Gone. Epi stands for Ecological Performance Indicator, which is actually a network designed by our overseeing government to actually check all our devices and all our structures and all our wastewater treatment plants, because we are the major wastewater treatment plant operator within the Flanders, which is the northern of Belgium. And the second part, GONE, it stands for Guiding Overflowing Network. For this, this will come clear further on. So one of the things which our overseeing government is checking us is our throttle structures, if they are working perfectly. For example, voltages, throttle pipes, we have around 1500, which is quite a big amount. If we all need to check them, it's almost impossible. You need a lot of meters, which is kind of difficult and cost assuming. So we first of all designed some kind of criteria to determine which throttles to actually look at, which are actually the most riskful to have some blockage, because these throttle structures are vital structures within our system, which restrict the flow to a certain amount, which can be seen here with an alpha and a beta value. In our case, this is 1.7 is beta and alpha is 6. So in total, it's around 10 times the dry weather flow. Due to these restrictions only happen during rain events and not during dry weather events. During dry weather events, the flow just passes on. During rain weather events, these structures block the water to prevent some overflowing at the wastewater treatment plant or at other streets and so on. So for this, we started measuring those devices. They have a simple QH relation, these structures. And for this, we started measuring them upstream and downstream of the pipe and the flow through the pipe. And we started measuring them, and we started also measuring an upstream overflow, because these structures are combined sewer overflows. And we measured this, and we saw that from a certain point on, we had really a lot of overflow, also during dry weather flow, which of course cannot happen due to our network, to our Epigone network. So we saw that there was something really bad happening. So first of all, of course, we solved this quite fast. It was already going on for about 16 days, which is in total, going to the river part, it was like 40% of what we normally distribute in our wastewater treatment plant effluent. So for this, you can of course measure all these throttle structures upstream, downstream, and measure the flow through them, but it's quite costly. So for this, we designed a different kind of system. So you see it's quite costly. So what we only need to measure actually is if there is the level rising during dry weather flow or not. Because at that moment we know that something is bad happening, something worse is happening, and we need to fix it at that moment. So what we only need to know is the water level, which is not so costly, which is a really safe system, almost no maintenance. And we need to know if it's raining or not. And the raining or not, we determine by radar image. This can be done in a different kind of system with just a rain gauge, but also that is quite costly. So actually using some kind of radar system, which is almost available, we could actually use this system to determine if it's raining or not. And from the moment we know if it's raining or not, then we can look at the levels and actually warn our people to go and have a look to see if there is a blockage and to solve this blockage. So that's where the GONE is coming from, because we actually look at overflows. So that's where the guarding overflow network is coming from. Thank you.
Thank you. Is there someone from the audience who has a question? No? Go on. Well, for how long are you running this system now? How long is this pilot running?
So the pilot itself, it's running for almost 4 or 5 months now. And so far we've detected no extra overflows, but so far we're down to the part where we start to implement more level meters, and every year there will be more and more coming. And the companies who sell the meters actually also give us the access to, via FTP to download the data easily, and in this sense we can easily react on it and we can easily work with the data.
Yeah, I would like to know what is the business case, let's say. How much do you invest in monitoring and how much you are going to gain, you expect?
The gain, I don't know, because there will be fees, of course, coming in the future. So far there are not, but in the future there will be. So I don't know what the gain will be, and the cost, yeah. That's depending on how much of devices we will install. So that's also something which I cannot directly say. But it will be less than when we install a complete setup, which of course also needs some full power of 220 volts, while, for example, the level meters only need to have a wireless connection, and that's already available via GSM modules and these kind of things. So it will be less costly than what we had in the past, but I cannot answer your question completely. I'm sorry for that.
Well, thank you very much for this attention.